Alright, so the first section that we're looking at is angles and their measure. So this is your introduction into trig. With these PDF lecture notes, this being your first one, you'll notice that there are some examples set up where they've been worked through, but what I want to focus on are the pieces that are at the back where I'm discussing the topics that are contained in this section. So when we talk about trig, we're talking about angles, talking about a lot about geometry. So I just want to cover some basics with you, where when we talk about symbols, like here you see this symbol here, this is our symbol for angle. So when you see this, it implies that we're talking about angle A. And usually when you write your triangles, you're going to see that they use capital letters to denote the angles in order for that to happen. If I have a situation where I have these two parallel lines and the transverse is going through them, and I want to correspond to angle DEF, then E is the middle, and we look at D as being where we start, E, and then over to F. The big thing about how we set angles up is that we always graph them moving up in a counterclockwise motion. So this is my initial side, and I move to the terminal side, and that creates this vertex. If I have a positive angle, I'm moving counterclockwise, such as in this case. If I'm having a negative angle, then we move clockwise. So in that case, this would be a negative angle because I'm moving clockwise in order to draw out that graph. For us, our angles are commonly labeled with theta and alpha, and then occasionally you're going to see a beta and a gamma. So just kind of keep that in mind. We have special angles. We have the right angle. You know, every corner in your house hopefully is built with the right angle. We have acute angles that are less than 90, and then an obtuse angle would be greater than 90. If an angle is in standard position, then that means that it has the initial side and the terminal side. And usually in a standard position assumes that it is a positive angle. But what we can see with these angles in this picture, you have the positive angle, which would be your standard, but then I can also move negative from this initial side and end up at the same terminal side. We call these coterminal angles because they share the same terminal side. So notice in this picture I have theta equals 135 degrees, but I can also have theta equals negative 225 degrees, and I'm going to end up at the same place. Definitions: complementary angles, they add to 90, and supplementary angles, they add to 180. And then here's just a brief review of some more geometry concepts. If these two lines are parallel to each other, and we draw that transverse line that cuts through both of them, then we get all these special relationships between the angles. The fact that these two vertex angles are equal, that angle 1 plus angle 2 would be supplementary because they add to 180 degrees, which is a straight line. We also know that opposite interior angles are equal, and that opposite exterior angles are also equal. With trig, you see that a little bit, so it's just something you want to keep in the back of your mind. When we look at trig, you're going to find that we measure a lot of stuff in radians. Degrees and radians are the common thing for trigonometry. If we take one trip around the circle, we consider that one revolution, which is 360 degrees, and that's labeled as 2 pi radians. The radian is the ratio of the circumference of the circle to the diameter. So we come up with 2 pi radians because it's based off of a unit circle. So if we want to convert between radians and degrees, then we use that conversion. The fact that 1/2 of a revolution is 180 degrees, which is also pi radians. So think about when you did conversions for like inches and feet, and you would say 12 inches equals 1 foot. This is the same type of conversion. So I can write them over each other, and it becomes my unit conversion. So depending on what you're looking for, and you want to be able to cancel labels like you do with unit conversions in geometry, then that will determine which one goes on top and which one goes on bottom. So I'm going to scroll back up to the top here where we did those. Notice that here I wanted to go from degrees to radians, so the degrees is in the denominator so that the degree labels cancel. Here I want to go from radians to degrees, so the radian is in the denominator so that those labels cancel. Another thing you'll notice is that those also said exact versus decimal answers. If I want an exact measure, there's no rounding or truncating, if you've heard that term before, and there are no decimals. An exact measurement will contain the symbol pi because you're not going to round off pi in order to get that answer. The approximate measure will be decimal answers. So when you do your work in my math lab, really pay attention to the blue directions because it's going to tell you they want exact measure or they want approximate, and when they say approximate, they will tell you how many decimals to round to. We have degrees, minutes, and seconds. We can do these on our graphing calculators. If we want to do them by hand, we look at the fact that 1 degree is 60 minutes and 1 minute is 60 seconds. So the 1 notch is a minute, 2 notches for seconds. So if I'm going the other way, if I have 1 minute, then that would be 1/60th of a degree, and 1 second then would be 1/3600th of a degree. Some quick applications that you're going to see in this class. It's not a physics class, so we don't really go into a lot of depth, even when we're talking about vectors and simple harmonic motion later. We will just touch on these subjects, but enough to where you're going to be able to say, I've seen them and I've worked with them. So arc length is S equals R times theta. Theta always has to be in radians. So if they tell you that the angle that cuts into the circle is 36 degrees, you need to convert that degree into radian measure using the conversion we just discussed. Arc length is this distance. So when I draw the angle, and it's cutting through this circle, what is this distance from the initial side to the terminal side? If I straightened it out, what would it look like? So that's when we talk about arc length. One thing that you're going to have to learn is the unit circle. It is imperative that it's memorized. So when you take your proctored exams, I do expect you to know this, and you will be given a quiz over being able to write the unit circle out. For right now, I want you to look at just being able to identify where our main or special angles are located, as well as their conversion. So when I look at 0 degrees at my starting, 0 radians. 30 degrees is pi over 6 radians. 45 degrees is pi over 4. I can find these conversions by using those conversion factors, but the more you work with these, the more they will become second nature, and I really expect you to know them. Not just memorize, but to know them. To know that if I'm at 270 degrees, that is also 3 pi over 2. So I don't have to know the coordinates right now. It's just being able to identify where these special angles are at and their radian and their degree numbers. Lastly, when you're looking at working with linear and angular speeds, the formulas are up here. When we look at linear speed, we're talking about if I have a point on the circle, how fast is that point moving? So if you think about your CDs and your instrument that's reading that music, how fast is that point traveling around the circle in order to create that sound? Angular speed says how fast is theta changing? As this point P moves around the circle, how fast is the angle moving as P moves? So it's all denoted. This is also a measurement in radians. So if theta is given to you in degrees, you must convert. Linear speed, V, is r theta over t, and angular speed, this is omega is equal to theta over t. So notice that the formula for angular speed is actually built into linear speed. So although this is a really quick overview, I just wanted to give you a look into what we're looking at as we begin our trip.